3.2, apply properties of rational exponents. These are going to be the same rules that we used in chapter 2, except we have rational exponents, which means fractions. I am multiplying like bases, so I add my exponents. What is the rule for adding fractions? I need a common denominator, which they have. This is going to be 4 to the 6 halves, and then 6 halves equals 3, so we get 4 cubed, and 4 times 4 is 16, times 4 is 64. We have a power being raised to a power, so we multiply those exponents. This is going to be 2 to the 8 times 1/4. Make this a fraction, multiply straight across, or cancel. I could cancel my 4 and my 8, but I'm just going to multiply straight across right now, and we get 8/4, which equals 2 to the 8 divided by 4 is 2, and 2 squared is 4. We have a product being raised to a power, which means that each one of these need to be raised to that power. Here we have 25 to the 1/2 times 4 to the 1/2. So that is 25 to the 1/2 times 4 to the 1/2. Here we can change our exponents into radical form. A half is known as the square root. The 1 stays with the 25, and 2 is the index number. So that would be the square root of 25 to the 1 power times the square root of 4 to the 1 power. The square root of 25 is 5 times the square root of 4 is 2, and this equals 10. I don't need to worry about 2 answers right now because I am not solving a square root. I am just simplifying. 8 to the negative 1/3. I'm going to start by taking care of that negative exponent. That's going to be 1 over 8 to the 1/3. There are a couple of different ways that I can go here. I could do what we did in the previous section and change this 8 into a 2 cubed, or I can think about what is this in its radical form. This is going to be 1 divided by, this is my index number, the cubed root of 8. And the cubed root of 8 is 2. This is 1/2. We are dividing with like bases. They both have a base of 9. And the rule for dividing is to subtract those exponents. Where are most of my 9s? I have 5/8 of them here and 1/8 in the denominator. I'm going to move my 1/8 to the numerator. That'll be 9 to the 5/8 times 9 to the negative 1/8. Changing the sign of the exponent when I move it to the numerator. Now we're back to the property of multiplying like bases, and so we add those exponents. We get 9 to the 5/8 minus 1/8 is 4/8. 4/8 is reduced to 1/2. And then we know that this is the square root of 9. And the square root of 9 equals 3. We have the quotient being raised to the power, so we need to make sure that both the a and the b are being raised to that exponent. This will be 16 to the 1/4 divided by 81 to the 1/4. We can change this into their radical form. That is going to be the 4th root of 16 divided by the 4th root of 81. The 4th root of 16 is 2. and the fourth root of 81 is 3. We are multiplying like bases. We add our exponents. This is going to be, we need to add 1/4 and 1/2. We need a common denominator. Again, I'm sure you know it's 3/4, but here our common denominator is 4, and then we get 2/4. So that's 7 to the 1/4 times 7 to the 2/4. That'll be 7 to the 3/4. How do I know that this is simplified? I have a fraction and it's not top heavy. If I looked at the fourth root of 7 cubed, well, the fourth root says that I have to have 4 of something under the radicand, and I only have 3 sevens. I don't have enough sevens to be able to work out to the fourth root. I know my answer is reduced and simplified. All right, now we have a product being raised to a power. I could start with the product and find that common denominator and combine these together, but I think I'll go and raise it to the power first. So that's going to be 6 to the 1/2 raised to the second power times 6 to the 1/3 raised to the second power. I have a power being raised to a power, so I multiply them. And you get 6 to the 1/2 times 2. Half of 2 is 1. Times 6 to the 1/3 raised to the second power. I need to multiply those exponents, and I would get 6 to the 2/3. And now I need to have a common denominator in order to add my exponents. I'm multiplying like bases. This is going to be 3/3. So I have 6 to the 3/3 times 6 to the 2/3. 3/3 plus 2/3 is 5/3. I see that I have an improper fraction. That means I'm going to be able to reduce. This is going to be 6 to the 5th, and the root is 3. So the third root of 6 to the 5th. Well, third root means that I need to have 3 of something under here, and clearly I do. This can be rewritten as the third root of 6 to the 3rd power times 6 squared. I'm adding those exponents to get 5. There's 3 of them that are going to work out evenly, and then I'm still going to have 2 left underneath the radicand. What is the cubed root of 6 to the 3rd? I already know that I'm going to have 6 squared, the third root of 6 squared. I know that's my answer. The third root of 6 squared. What is the answer to the third root of 6 to the 3rd? That's 6 to the 3rd, and if I change it back to its fractional exponent, that's going to be 1/3. I could put a 1 around all of this, and it would be 1 divided by the 3. Well, 3 times 1/3 is going to be just 6. And to simplify a little bit more, we get 6 cubed roots of 36. Very tedious. There's many ways to go about this problem. As long as we all end up at the same answer, we're good. Five divided by 5 to the 1/3. Well, we have an exponent here of 1, but I want it to have a common denominator with 1/3. So I'm going to say 5 to the 3/3. 5 to the 3/3 divided by 5 to the 1/3 equals 5 to the 3/3. I'm going to change the sign on this exponent, which is going to be negative 1/3. 3/3 minus 1/3 is 2/3. 5 to the 2/3. It's a proper fraction. It's not improper. When I get an improper fraction, that lets me know there's going to be some reducing here. How many times can 3 go into 5? Once. We get 1/6. And there is 2/3 left over. 42 to the 1/3, 6 to the 1/3, and it's all being raised to the second power. So we have 42 to the 1/3 being raised to the second power, divided by 6 to the 1/3 being raised to the second power. 42, power to a power, we're going to multiply those exponents. 1/3 times 2 is 2/3. 6 to the 2/3. I like 42 divided by 6. And so I'm going to take where we have the same rational exponent, and I'm going to change this into 42 divided by 6 raised to the 2/3. If I applied that power rule, it'd still be 42 to the 2/3 divided by 6 to the 2/3. But this allows me to reduce 42 divided by 6. And we get 7 to the 2/3. This is a proper fraction. I am fully reduced. Use rational exponent properties to simplify. So they're not telling me which form to put it in. If they want it in radicand form, then I would change it. But 7 and 2/3 is fine. A lot of algebra in these exponents, manipulating. Hopefully you have a good understanding from chapter 2, the rules for exponents. As you can see, it's going to be more in depth for this chapter. Properties of radicals. This only applies to multiplying and dividing. We have the product property. We can see that when we have the nth root of a times b, I can rewrite that as the nth root of a times the nth root of b. I can take them apart and I can put them back together. The same for dividing. We can take the nth root of a divided by b and break it up as the nth root of a divided by the nth root of b. Again, we can take them apart and we can put them back together. I have the cube root of 12 times the cube root of 18. Are there any perfect cube roots in there? There are not, so I'd like to put them together. Cube root. And I'd also like to factor them down into prime numbers so I can see what's going on here. I have 4 times 12. I know 4 is not prime. We have 4 times 3 in this one, and then we have 6 times 3 for 18. And again, if I continue to break that down, that would be 2 times 2 for the 4, and then 2 times 3 for the 6. And now I can really see all of the prime numbers and how many of them I have. I want 3 of them. So I'd like to group them together by 3s. Let's see, I have 1, 2, 3 2s, that's 2 cubed. And then I have 1, 2, 3, 3 3s. And that is the cubed root. The cubed root of 2 cubed is 2. The cubed root of 3, the cubed root of 3 cubed is 3. That totally equals 6. So the cubed root of 8 is 2. The cubed root of 27 is 3. And then you multiply them together because that's what was happening under the radicand. We have the fourth root for both of them. And there is no perfect root, fourth root for 5. Let's put them together under the same radicand. And we have 80 divided by 5. Let's do that division, see what we get. It's going to be the fourth root of 16. And then does the fourth root of 16 work out evenly? A radical with an index of n is in simplest form if the radicand has no perfect nth powers as factors and any denominator has been rationalized. Here we go again with rationalizing the denominator. You can't leave square roots in the denominator, or cube roots, or any other root for that matter. All right, the cube root of 135. We need to simplify it just like we did in the previous example. So I'm going to look for all the prime factors of 135. We have 135 using the upside down division bar, all prime numbers on the outside. It ends in a 5. So we'll use 5. 5 goes into 13 twice for 10. There's 3 left over. 5 into 35 is 7. And now I know that 27 is going to be 3 cubed. We have 5 times 3 cubed. The cube root of all of that. 3. What is the cube root of 3 cubed? Or what is the cube root of 27? That's going to be 3. And then we do not have enough 5s, and so that stays underneath the radicand. We have the 5th root of 7 and the 5th root of 8. All right, so we only have 1 7, but technically how many of something do we have being raised to the 5th power? We know that we have the 5th root of 7, and we have the 5th root of something. How about 2 cubed? There are 3 2's under the radicand of the 5th root. All we need is 2 more 2's, and it would work out evenly in the denominator. And that is what we want. Let's put all of this together underneath the same radicand. And we have 7 divided by 2 cubed. We only need 2 more 2's, so I'm going to multiply by 2 squared. Whatever I do to the denominator, I got to do the same thing to the numerator. Now I have the 5th root of 7 times 4 is 28. And 2 to the 3rd power times 2 to the 2nd power is 2 to the, add your exponents, 2 to the 5th power. Now we have our denominator working out evenly. I have 5 2's. So what is the 5th root of 2 to the 5th? That is going to be 2. And then we still have the numerator, the 5th root of 28, which is only 7 times 4. There's not enough of anything to reduce. Final answer, we do not have a root in the denominator. It's been rationalized. Final answer. Now, what can we do with adding and subtracting? We can add roots together if they're the same root. It would be like adding 2x plus 4x. When I have the same kind of variable exactly, I know that I can combine those together. Well, that is also true for roots. If I have exactly the same root, I have the 4th root and the 4th root. The 4th root of 10, the 4th root of 10. They're exactly the same. That means I'm going to look out front and I'm going to combine their coefficients. There's an understood to be a 1 out front of this 4th root of 10. So we're looking at 1 plus 7. Those are the coefficients. I have exactly the same root. It has to be exactly the same. A has to be the same, and the n has to be the same. This is going to equal 1 plus 7. And we have the 4th root of 10. So we get 8 4th roots of 10. Final answer. It's exactly like adding variables that have exactly x to the 1, x to the 1. I know that I can add those coefficients. Now we have 2 times 8 to the 1/5 plus 10 times 8 to the 1/5. Do I have exactly the same 8 to the 1/5? That is the 5th root of 8. Remember, we can change our roots into fractional exponents. So this is just going to equal 2 plus 10 is 12, 8 to the 1/5. I can add radicands, and I can add fractional exponents that have the same base. I have the cube root of 54 minus the cube root of 2. I have a 1 out front of both of these, so I guess that's, what is that? Do I have exactly the same? I do not. I need to have a cube root of 2 if I'm going to combine it with anything else. That means we need to look at reducing the cube root of 54. All right, the cube root of 54, we're going to break it down. This is an even number, so I know 2 goes in, and I also know 3 goes into 54. The divisibility rule for 3 is you add up your digits. 5 plus 4 is 9, and 3 can go into 9. Therefore, 3 can go into 54. All right, let's do 3. 3 goes into 5 once. There's 2 left over. 3 into 24 is 8. I could do a 3 again. And we get 3 into 18 is 6. Do another 3. 3 into 6 is 2. I have a prime number at the end, therefore I'm done. So we have 3 cubed times 2. We have the cube root of 3 cubed times 2 minus the cube root of 2. Here we can see the cube root of 27 is going to be 3. We have the cube root of 27 is 3. And then what's left? We have the cube root of 2 minus the cube root of 2. We have 3 times the cube root of 2 minus the cube root of 2. Now that we have exactly the same radicand numbers, and we have the same a values, we can combine that together. Remember that there is a 1 understood to be in front of the radicand. So we're looking at 3 minus 1, cube roots of 2. 3 minus 1 is 2, and we have the cube root of 2. Simplify the expression. I would like to see all cubes in here, so I can see exactly what's working out evenly, because we're working with a cubed root. 64, what does that break down to as a cubed? That's going to be 4 cubed. And now how can I write y to the 6th to make it look like it has a cube? We have y to the 3rd times y to the 3rd. That means that all of these are going to work out evenly. We have a cubed root. We have 3 4s, 3 y's, and 3 y's again. The cube root of 64 is 4. The cube root of y cubed is y. And the cube root of y cubed is y again. My final answer is 4y squared. We have a cube root here again. This would be the cubed root. And we can see that we have multiples of 3 here. That's good. And I'd like to change 27 into an exponent. That's going to be 3 cubed, e cubed, and q to the 12th, all being raised to 1/3. Remember that 1/3 is going to be a cubed root. I can divide all of my exponents by 3. I could have done it here. Dividing by 3, we get y to the 1. Dividing by 3, we get y to the 1, or back to the beginning. Dividing by 3, we get y squared. And this is why, because we can go from radicands to their fractional exponents. That is why you're dividing by 3 to have it work out evenly. These are all being multiplied by 1/3, which is the same thing as dividing by 3. 3 to the 1/3 is going to be 3 to the 1 power. P cubed being raised to the 1/3 power is going to be P to the 1. Q to the 12th power being raised to the 1/3 power is going to be Q to the 4th power. 3P Q to the 4th. Now that we know when we have a radicand, we can actually just divide the exponent because really you're multiplying by 1/3. Here we have the 4th power, so that means that would be raised to the 1/4 power. If I changed it into its equivalent form of a fractional exponent, we'd be dividing by 4. So are these multiples of 4? This is going to be m to the 4th divided by that 4. We get m to the 1. And then n to the 8th divided by that 4 is going to be n squared. We don't have any parentheses around this, grouping this all together. These are all individual. We have 14 divided by 2, x divided by x to the 3/4, y to the 1/3 divided by no y's, and z. All right. Here we go. I'm going to space this out a little bit. Let's go with 14. And that's going to go with our 2. We have an x to the 1 power and an x to the 3/4. Those will be going together. We have a y to the 1/3, not paired up with anything. And then we have a z to the -6. 14 divided by 2 is 7. Now, where are most of our x's? Because I don't want to have a negative exponent. I have a 1 up here. And so what is that common denominator for 1 and then 3/4? That's going to be 4/4. So I would like to bring my x to the 3/4 to the numerator. We have x to the 4/4. And when I bring 3/4 up, that's a -3/4. And then we still have y to the 1/3. And we have a negative exponent. Z to the -6 will be z to the +6 when I bring it to the numerator. It's just piece by piece. Tedious, yes. Not that difficult when you take it piece by piece. Our final answer is going to be 7x. 4/4 minus 3/4 is 1/4. Y to the 1/3. And z to the 6th. Write the expression in simplest form. For the 5th root of 4, that is not going to reduce. That'll have to stay. How about the 5th root of a to the 8th? Let's rewrite that as a to the 5th times a to the 3rd. Adding those exponents to get a to the 8th. I can see that this a to the 5th is going to work out evenly. B to the 14th. What is a multiple of 5? B to the 14th. That would be b to the 10 would work out evenly. And then we still have 4 of them that will be left. C to the 5th. That all works out evenly. All right, what do we have? The 5th root of 4, a to the 5th. The 5th root of a to the 5th is a. And then we have a cubed left. The 5th root of b to the 10, remember you're dividing the exponents. 10 divided by 5 is 2, so that's b squared. And then we have b to the 4th left. And then the 5th root of c to the 5th, 5 divided by 5 is 1. So we have just a c left out there. Now we have a third root. We don't have enough x's. Here we have 8 y's. But remember, we can't leave anything in the denominator. How many more y's would I need in order to work out evenly? Has to be a multiple of 3. So if I multiply by 1 more y, I'd have to do the same thing to the numerator. Now I have y to the 8th times y, and that's y to the 9th. Cubed root of xy divided by y to the 9th. Now we're ready to take that cube root. We have the cubed root of xy divided by, what is the cube root of y to the 9th? Well, divide by 3, and we get y cubed. The denominator has been rationalized with no radicands left in the denominator. Perform the indicated operation. We have 1/5 square root of w plus 3/5 the square root of w. For adding and subtracting, we need to have exactly the same radicand. And we do. We have the square root of w and the square root of w. We're just going to add those coefficients. 1/5 plus 3/5 is 4/5 square root of w. Now we have 3xy to the 1/4 minus 8xy to the 1/4. Do we have exactly the same variables? We have x, y to the 1/4, and an x, y to the 1/4. We have exactly the same variables. We're going to subtract those coefficients. 3 minus 8, we get negative 5 x, y to the 1/4. All right, we have a cubed root, and we have 2z to the 5th and 54z squared. They need to be exactly the same. Let's try reducing down the cube root. All right, we have a 2 that's going to stay in there, and then we have z to the 5th. How can we split that up to work out evenly? That would be z to the 3rd, and then we have z squared. It still adds to 5. Minus z on the outside, and we have the cubed root 54. We need to break down 54. 54 is 9 times 6, so that's 3 times 3. 9 times 6, that's 3 times 3, and 3 times 2, we have 3 3s. So we have 3 cubed times a 2 times z squared. We don't have enough z squares. All right, let's reduce. 12. What do we have that's coming out of the cubed root? We have z cubed. What is the cubed root of z cubed? That's z. The 2 stays and the z squared stays. We have the cubed root of 2z squared minus, we have 3 cubed, so the cubed root of 3 cubed is 3. The 2 stays, the z squared stays, so that's all that's coming out. And then we do have a z out front. And we have 2z squared left. Do we have the same exactly? We have exactly z times the cubed root of 2z squared, z times the cubed root of 2z squared. We have exactly the same variables, the same index numbers, the same a value. Therefore, we can just combine those leading coefficients. 12 minus 3 is going to be 9z cubed root of 2z squared. Final answer.